Things are well. Okay, so start broadcasting and let's start. Not this, not this. Okay. So GH200 and today is February 15th, 2021. So today we'll do uniform and Gaussian distributions. Also, I have one announcement. Quiz 3 will take place next Monday, February 22nd, and it will be last quiz before midterm. Okay. With that said, I think we are ready to start our lecture. Let me just recap what we did last time. Question?
Doctor, just before we start, can you please tell us what will be covered in the midterm? What are the materials that will be covered in the midterm?
At least up to the end of the lectures of next week. We'll have this week we'll finish continuous distribution. Joint distribution will be for sure in the midterm. So up to the lectures till the end of next week, because next week will be maybe more. No, maybe more. So we have the midterm is March 1st, right? So next Monday is 22nd. Or the following Monday, 2 weeks from today. Yeah, so till the end of the lectures of next week will be covered. So most probably until the end of the joint distributions. I will talk about the midterm early next week. I will post samples and maybe we'll do one review session before the midterm, inshallah. Hi. Last time we finished. We talked about how to characterize a continuous random variable. And we mentioned many ways. We talked first about small f of x, and we mentioned how to define f of x in the continuous domain as opposed to the to defining it in the discrete domain. If you recall, in the discrete domain we always said that f of x itself is a probability, but in the continuous domain f of x itself is not a probability but is used to calculate probability. So it's not defined as fx equals something. The way we define it is that the probability of the random variable to be between two values a and b, we just integrate small f of x over that range to get the probability of the random variable to be in that range. And the only condition on f of x is to be positive. In principle, f of x in the continuous domain, its value can be greater than 1 because its value does not matter. What matters is the area under the curve. So the way to check whether we have a valid f of x or not is just to check the area under the curve of f of x, whether it's 1 or not. So this is the first way to characterize the the random variable, and this is what we call BDF, or probability density function. The second way is the mean, or expected value of E of x, and the way we define it is just minus infinity to infinity x f of x dx. And again, this is opposed to summation of x times f of x in the discrete domain. And the mean tells about the location of the random variable, as we mentioned before. Talked about also the variance, or v of x, or sometimes we call it expected value of x minus mu squared. And again, the way we define it is just integration from minus infinity to infinity of x minus mu squared f of x dx, or a simpler way to do it is x squared f of x dx minus mu squared. Finally, capital F of x, or the CDF, what we call the CDF, cumulative distribution function, and it's defined exactly in the same way as in the discrete domain, but in this case the way we calculate it is different. The way we calculate it, we use an integration instead of a summation. We integrate small f of x from minus infinity to the value that we are interested in, and we established this relation between small f of x and capital F of x last time. So it's d f of x by dx. So we just take the derivative of capital F of x to get small f of x, and we talked about properties of capital F of x. Of course, it's at infinity it's 1, at minus infinity is 0. The reason is that, just go to the definition, what's f of plus infinity? Means that what are the chances that the value of my random variable is less than infinity, plus infinity. For sure, any random variable will take a value less than plus infinity. So this probability is 1. What's the probability that it has a value less than infinity? This is impossible. So that's why this is always 0, regardless of what random variable we are talking about. Let's do a quick example, and then we move to today's topic. A quick example. Given the following capital F of x, assume that I'm giving you capital F of x as given like this. So 0, if x is less than 0, 0.2x when x is between 0 and 4, 0.04x plus 0.64 when x is between 4 and 9, and 1 when x is greater than or equal to 9. So I'm giving you a certain capital F of x. Of course, you can draw this if you want. X, this is capital F of x. So before 0, it's 0. From 0 to 4, it's a straight line. So it goes from 0.2 times 0, 0, all the way to 0.2 times 4 is 0.8. So it goes down to 0.8. And then at between 4 and 9, it's another straight line that go all the way to 1. So at 4, it is 0.8, and this is how it look like, and then it will continue at 1 to infinity like this. So this is capital F of x. Now I can ask you, what's small f of x? Find f of x. How do you find small f of x?
Find the derivative.
Establish the relation. Yeah. we establish the relation between them. And I see some question in the chat. Please check your syllabus. Every time people ask me how many quizzes we'll have, it's all in the syllabus. As I said before, we have 5 or 6 quizzes. I will take best 4. Okay, so we'll have best 4 quizzes out of 5 or out of 6. So to find small f of x, we just take the derivative. So if you take the derivative, so derivative of 0 is 0. Derivative of 0.2x is 0.2. Derivative of 0.04x is 0.04. And derivative of 1 is 0. So let's sorry. Let's try to plot small f of x. How does it look like? Again, at 0. At 0, between 0 and 4, it's fixed to 0.2. And between 4, let me remove this line. Between 4 and 9, it has a smaller value like this. So it is 0.04. How do we check if this is a valid probability density function?
And the area
This
under
whole
the curve.
area should be, area under the curve should be 1. So how do we calculate it? These are 2 rectangles. So this is 4 times 2, 0.2, which is 0.8. And this is 5 times 0.04, which is 0.2. So indeed, area is 1. What's the mean? If I ask you to calculate the mean, just use the definition. Again, it's x f of x. By the way, do you expect the mean to be greater than 4 or less than 4?
Less than 4.
Less than.
Why less than 4?
Because before x equal 4, the magnitude is bigger or the area is bigger. So
yeah, logically, يعني, if you see it, the balance is more to the left.
Yeah, so we have more probability less than 4. So if we look at the mean, as we mentioned before, a way to balance this, so it should be less than 4. So applying the definition again, so I have 2 ranges from 0 to 4. I have x times 0.2 dx plus, and then from 4 to 9, I have 0.04 x dx, and you just solve this. I will not solve it, so just 0.2 x squared over 2 from 0 to 4 plus 0.04 x squared over 2 from 4 to 9. And if you solve it, you will see that this is a number less than 4. Okay, so done with talking generally about random variable in a generic fashion. Let's start with talking about, like we mentioned last time, scientists, they made our life easy. They studied several random scenarios and came up with certain families or certain distributions that can describe random phenomena that we face in our daily life. So, and here we will study 3 continuous random variables. Hopefully today we'll do 2 of them, or at least 1.5, and then on Wednesday we'll continue the rest, so that we are ready to do the joint distribution next week. So let's start with the first one, which is the continuous uniform distribution. And continuous uniform distribution is somehow is similar to what we did in the discrete domain. Discrete domain, if you recall, we assume that all probabilities have the equal probabilities, or the outcomes of an experiment have equal probabilities. However, in the continuous domain, we do not have points to give them probabilities. So the uniform distribution here, uniform distribution, entails that equal ranges have equal probabilities. And that f of x is a flat curve. So f of x is just a straight line, horizontal line. It does not go up and down because all ranges have equal probability. So a continuous uniform distribution is given by f of x is simply 1 over b minus a when x is between a and b and 0 otherwise, and we write it uniform of a and b. So, or x is uniform between a and b. How does this look like? Probably if we plot it, it will look much better. So if this is x, this is f of x. So if we say I have a uniform distribution between a and b, then it looks like this. So it's a straight line, and the height is just 1 over b minus a. Why 1 over b minus a? Because again, the area should be 1, and we know that this part is b minus a, so the height should be 1 over b minus a, so that I have an overall area of 1. So area again, area of 1. Okay. Type. Can you guess what's the mean of a uniform distribution?
b minus a over 2.
B minus a over 2. Are you sure?
b plus a over 2.
Yes.
B plus a over 2.
Why, doctor?
Which is the middle point. Why? Let's see. What's the mean? You can, if you have between 4 and 7, between 3 and 7, what's the middle point between 3 and 7? It's 7 plus 3, 10 over 2, which is 5, right? It's not 7 minus 3, 4 over 2, which is 2. If you want to have the middle point between two numbers, you just add them and divide by 2, right? But if you don't want that, you can just apply the rule of the mean, which is x f of x dx, which is very easy to prove in this case. So integration from a to b, x, what's f of x? We know that f of x is 1 over b minus a dx. So this is simply x squared over 2 b minus a, and then from a to b. So this is simply b squared minus a squared over 2 times b minus a. And we know that b squared minus a squared is just what is b minus a times. You can expand it like this, and you can cancel, and then you can simply prove that this is b plus a over 2. So this is the mean of the uniform distribution. It's very simple. The variance, sigma square, is just, you can show that it is, this is also easy to prove. I will not prove it, but it is easy to prove. Okay. Let's do a quick example. Uniform is easy. We will not spend a lot of time on the uniform. But in real life, uniform is sometimes used to model the error. Like the example that I came up with this morning. Let me repeat it here. Assume that the error in the diameter of a metal ring is uniformly distributed between minus 0.1 and 0.1 with a nominal value for the diameter is 1 centimeter. So this, we're talking about cheap rings that you buy to like washers, the door that you use in everyday life. So exact diameter is not that important. So this can be 1 centimeter plus minus 0.1 centimeter. So what's the range of diameter? Diameter can be as low as what? 1.1. So the diameter itself, is also uniformly distributed, right? So diameter itself is uniform between 0.9 and 1.1. The error is uniform between minus 0.1 and 0.1, yes, right? So both are uniform. So what is f of x for the error? So the error, if we plot it, it's between minus 0.1 to 0.1. This is x. This is f of x. What's f of x? What's the value? Anyone? Equals what when x is between 0.1 and minus 0.1 and 0 otherwise? What's the value?
One.
Again, how do we find it? What should be this area? Area should
1
be
over b minus a.
Equal 1.
Yeah, 1 over b minus a.
Is 1 over
Is it 1? 1 over
which
b
is
minus
5.
a is what?
It's 5.
5, right?
Oh, yeah. This is 5. So it's 1 over 0.1 minus 0.1, which is 5. So this is the value of f of x. Don't tell me that this is greater than 1. I see, and some of you خايفين, if you are scared because it's greater than 1. In continuous, we said the value of f of x, it's okay to be greater than 1. What matters is the area. Any area cannot be greater than 1. The value of f of x can be greater than 1. What's the mean?
0.
Mean is 0, yeah? And if you want to apply again the rule, 0.1 plus minus 0.1 over 2, which is 0, and sigma square, which is the variance, is simply b minus a squared over 12, which is 0.1 plus 0.1 minus 0.1 squared over 12, so it's 0.2 squared over 12. And yeah, that's it for the uniform distribution. The last point that we need to mention is the CDF. What is capital F of X for a uniform distribution? For uniform distribution, like any other distribution, what's the definition of f of x? Is just the integration from minus infinity to x, f of u du, right? Which is, we know that the uniform starts at a, so it's integration from a to x, and the BDF is 1 over b minus a du. So you integrate this, so you have u over b minus a, and then you substitute from a to x. So this is simply what? X minus a over b minus a. So f of x is simply x minus a over b minus a when x is between a and b, 1 when x is greater than b, 0 when x is less than a. If this is my, if this is our small f of x, then the capital F of x we know that capital of x should start at 0 somewhere, so it will go all the way until you reach a. Between a and b, you just have what? The equation of a line, because if you have a constant, you integrate a constant, then you get line. So between a and b, it moves all the way to 1, and then you continue 1 till infinity. Right? We all agree that capital F of x should start at 0 and should end at infinity. Okay. So enough with the uniform, and probably this is a good point to stop and take the. Let me.
Doctor?
What is it? Yes.
Yeah, you wrote from
تفضل.
A to A.
From A to A, right? It's not غلط from A to A.
ما أدري يعني مو بالأحسن من A to B يعني.
A to B أحسن صحيح.
تمام.
I agree. طيب, please log into your Blackboard. I'm starting the attendance shortly, and you'll have 1 or 2 minutes to finalize your attendance. You know. Okay, I started the check-in. Please check in your attendance so that we can start with the normal distribution.
Doctor,
Yes.
before we go to the next point, I have a question. about the previous point. Now the probability of X being after B should be 1, right?
No, what exactly you are saying? Probability of X greater than B?
Yes. Or 0.
يلا أنت tell me what's probability of X greater than B is what? Is 1 minus probability of X less than B, right?
Mm.
Which
So it should be
means
0. But
1 minus f of B, which is 1 minus 1, which is 0, right?
yeah, that's why I asked this question, because I saw you solved it in the previous lecture, but I didn't understand why. What does that conceptually mean?
Conceptually mean, you know that A, your random variable, it's only the range of your random variable is only between A and B. If you say what's the probability that it's greater than B, it does not exist. What's the probability that it's less than A? It does not exist there. So probability of X less than A or greater than B, it's 0 for sure.
Okay. I thought
It does not
it
exist
means
there.
it
Only
exists beyond B. Okay, now it's clear. Thank you, Doctor.
sure. Okay, I think you had enough time. There's still 1 minute for those who were not able to check in up to now. I see a couple of students just logged in to mark their attendance. It's I don't know. I can track those who just check into log into to the attendance, and there's no marks on attendance. And please just attend and try to understand the material. Okay. Okay, so let's, what's wrong? I want this. Okay. Normal or Gaussian distribution. Normal or the Gaussian distribution is the most important distribution that we will study in this course, and it will continue with us till the end of the course, as you will see. It will, even when we start the statistics part of the course, Gaussian distribution plays a key role over there. Okay, so normal is the most important distribution, and this is the distribution that you guys keep complaining at when faculty members, they said they use the curve for grading. So it's the normal curve or the Gaussian curve, the most important distribution. Why it's important? Mainly for 2 reasons. So why important? First reason it's important, it's because Gaussian distribution or the normal distribution, let me stick to the normal, I think it's more popular. Normal distribution characterizes many natural phenomena that we exist in our real life. So if we talk about the weights of people, if we manage to weight everyone in Qatar, or even everyone in Qatar University. Qatar University is a big community. We have 20,000 students, 22,000 students, like 3,000, 4,000 employees. So if we manage to weight everyone in Qatar University and plot a histogram, we talk about histograms in 2 chapters, the distribution will follow a normal distribution. The height of people, the grades of students in large groups. So in this course, for example, we have 2 groups. I will give you the same midterm exam. So I will end up with 80 plus, almost 90 students. So I expect, I will not force it to be a normal distribution, but I expect that the distribution of grades will be normal. What does that mean? In all of those examples, it means that there's a small group that they will do really well. There's a small group that they will do really bad. and then in the mid, most of the people are normal in the middle. It's the same for weights. We have very small number of students. I can't see now number of students. I cannot pick up on you, but we have few students who are really overweight. We have few students who are really underweight, and most of the students are in the middle, around the average weight of people. Same for heights, and same for like many of the natural phenomena. That's how Allah has created us. So the first thing why normal distribution is important, because it characterizes many natural phenomena like weight, height, grades, and so on. In our fields, it also characterizes many errors. Like in the lab, if you did the circuit lab, or for those of you who take electronics lab, we have a famous noise called thermal noise that's caused by the movement of electrons in wires, random movement of electrons. It's also characterized by a normal distribution. Type. So this is the first reason. What's the second reason? Second reason is very, very interesting thing. It has to do with a theorem which is called the central limit theorem. We'll talk about it later on in a future chapter. But the central limit theorem very simply says that if you add large number of different random variables, you will end up with the result of the summation is a normal distribution. So even if you add even if you add discrete random variables, you will end up with normal distribution. So if you add even uniform, we just saw the uniform. If you add 2 uniforms or 5 uniforms, you will get very close to a normal distribution. Of course, adding random variables is done in a certain way. We'll talk about it, I guess. And in your next computer assignment, you will do a very small simulation that you will verify yourself that when we add different random variables, they will add to a normal distribution. So central limit theorem says if you add large number of, I will say, normalized random variables, the result is normal. And in our research, in my research area, and in many other research areas, every time we face a random phenomena that we cannot model or we do not fully understand, it's very common to assume that it follows a normal distribution. It's the most popular assumption in probably in research, to assume the noise that you don't know, the interference that you don't know, the certain effects of impairments, of hardware impairments, software impairments. All of this usually are modeled by a normal distribution. Right. So this is the normal distribution. How does it? What's the equation for the normal distribution? PDF of a normal distribution. It has a bit of nasty PDF. It's not that nice, but somehow if you use it a lot, you'll come to memorize it. F of x can be written as 1 over square root of 2 pi sigma squared, and then e to the minus x minus mu squared over 2 sigma squared, and x is between minus infinity, plus infinity and minus infinity. So this is the PDF of a normal distribution, where in this equation mu is the mean and sigma square is the variance. So for the normal distribution, you can right away tell what's the mean and what's the variance by looking at its f of x. You don't need to calculate it. You just look at it and you can tell that it is mean is certain value and the variance is certain value. And we usually write it as normal of mu and sigma square. So for example, if I tell you write down a normal distribution that has a mean of 1 and a variance of 4, you right away just write 1 over square root of sigma squared is 4, so 8 by e to the minus x minus 1 squared over 8. I can have another example. If I tell you given the below f of x is just 1 over 4 by e to the minus x minus e to the minus x squared over 4. And I tell you what is mu and sigma squared. Looking at the equation, what's the mean of this random variable, of this normal random variable?
0.
0. Just compare this to this. So if I have a mean, then it should be x minus something. I don't have that, then mu is 0. What's sigma square?
2.
4.
1.
2,
Oh.
right?
1,
2. Because 2 sigma square is 4. So sigma square is 2. Okay. Type. How does it look like if you put, how does it look like the normal distribution? It has a shape like a bell. So normal distribution will look something like this. Middle value is mu, and we'll see how is sigma related to the width of the normal distribution. But normal distribution, like any other distribution, we said the mu defines location, and sigma or sigma square defines what? Spread, right? So if I tell you plot those two curves, what's the difference between those two curves?
The location.
the location.
The location. So they are exactly the same.
Except
However,
that
one centered at 0 and one centered at 4. So if this is the
And the other center is at 3, Doctor, I think.
Or 3, yes. Yes, thank you. You're right. So this is this, and this is this. Can you see the shape of the curve? Is usually the normal curve is called the bell shape. It's like a bell, the jaras. That's why in 2 dimension the Gaussian is a real bell type. How about if I ask you plot normal of 0 and 4 and normal of 0 and 1? How would they look like? So let's see, the center of both is what?
0.
The mean of both is 0, right? So let me draw one, and then you will tell me how does the other one look like. So let me, this is not good. I want to do it. So if I tell you this is the normal of 0 and 1, how does the other one look like?
Same center, but but bigger width.
Bigger width, right? So is this right? What do you think?
I think, yeah.
I think it's right.
It is right. طيب نحن قلنا, we said that the area under any probability curve should be 1, right? Those 2 curves have different areas, right? The red one has larger area underneath.
Or
so one of them should be wrong.
The amplitude should be different.
Yes, so the red one is for sure is wrong.
Yeah.
The red one can't be like this. It should be something like
shorter,
so that its area is 1. So this area is 1, and the area for the other as well is also 1. طيب. Now there is an issue with normal distribution. Which is its f of x does not exist. There is no expression for capital F of x, which means that what's f of x? Now we define it. F of x is defined like this, right? Integration from minus infinity to x f of u du, which is in this case f of x is over 1 over 2 by sigma square e to the minus u minus mu squared over 2 sigma squared du. This integration cannot be calculated. Actually, if you try to do any integration that has e to the minus x squared, you will not be able to there's no solution for the integration of e to the minus x squared. So this, no expression for this. Right. And I know you are college students, so and engineers and computer scientists, so you know there is always a solution for everything. If we cannot integrate something in closed form, what do we do? Excuse me. None of you took the numerical analysis course?
No, I didn't.
We find the zeros.
We do what we call numerical integration, right? Have you heard about numerical integration?
I haven't, no.
No.
So numerical integration is a way to calculate any integration that you cannot calculate it in an expression form. So basically, like integration is always finding the area under the curve, right? And capital F of x is like finding the area from minus infinity to a certain x. So if you want to calculate this area and we don't know exactly how to do it, we just with numerical integration we divide it into whatever smaller areas, and then we approximate it by straight lines, and then we add the areas. So this will give you an approximation of the curve, of the area under the curve. So we can calculate f of x numerically and then tabulate it. Then what we can do, if we cannot calculate this, we do numerical integration. We go MATLAB does it. Mathematica is even more powerful than MATLAB in doing numerical integration. And then we have a table that, okay, what's f of 3 to that table, and then you for the value, and then you use it in your calculation. But what's the problem with this? There's another issue. Which is we have to do this for each combination of mu sigma square, right? So every time the mean changes, we have to go back and do the numerical integration and calculate things using the software to get results, which is not convenient because I have infinite combinations. Mu can be any number, sigma square can be any number. So I will not be able to create tables for every combination of mu and sigma. So what do? We use what we call the standard normal distribution. And we'll see how is that handy. What's a standard normal distribution? A normal distribution that has a mean of 1 and a mean of 0 and a variance of 1 is called a standard normal. So it's just annotation. I have a special normal distribution which has a mean of 0 and a variance of 1. I will call it a standard normal, and I will call it Z. So Z is what? Z is normal of 0 and 1. And we call its BDF f of Z less than Z. I will call it phi of Z. So what does this mean? It means I have a certain normal distribution that is centered at 0, which has sigma of 1, sigma square of 1. And now I will call, if this is Z, then the probability that Z is less than Z, which is the integration from minus infinity to Z f of x dx, I will call it phi of Z. Okay? So the area under the curve from minus infinity to any value, I will call it phi or phi, if you call it phi. I know many students, they call it phi, of that value. طيب, why is this good? Because we table for different values of Z is available almost everywhere, and in your book, in the appendix, there's also this table is available in your book and can be used to calculate f of x for, as we'll see, we can use this table to calculate the probability cumulative distribution function for any normal distribution. So again, this is very important. We defined what we call the standard normal distribution. What's a standard normal distribution? It's a normal distribution that has a mean of 0 and a variance of 1. So we define what we call it Z, and it's up to us. Now we call it Z. And then I will call it CDF. I will call it phi of Z. And phi of Z, what does it mean practically? It means the area under the standard normal curve from minus infinity to any value. So if I tell you, or if I ask you, what is phi of 0?
The area from minus infinity till 0.
Which is what? You should know it.
Half.
1/2, right?
Yes.
Why 1/2?
Yes.
Because the whole area is 1.
Because
So
the whole area is
Because
1.
it's centered
Normal,
at 0.
yeah. Normal is symmetric, so this is 1/2. What's phi of minus infinity?
To be 0.
0. Phi of infinity?
1.
1, right? So the area under the whole curve is 1. So phi of infinity, again, means what? Probability of Z less than infinity. This is probability of Z less than minus infinity. This is probability of Z less than 0. So, and using the tables, we can calculate phi of z for any value we are interested in. But let's see. Let me go to your. This is your book. Okay, this is your book. Soft copy of your book. And at the end of the book, there are many appendices. There is other tables that we will deal with later in the chapter, later in the course. But we have index or table appendix A, table 3. It tells you it has this table, as you can see. Let me see if I can delete some of those. Yeah, some can be deleted, some cannot be deleted. So as you can see in this table, it gives you, there's a Z on this corner. You can see it. I hope you will be able to see it. And then there are numbers here and numbers here. And your number, any number you are interested in, is composed of those two numbers. So, and the body of the table is the probabilities. So, for example, if we are interested in phi of minus 2.35, which is what? Which is the area under the Z curve all the way from minus infinity all the way to minus 2.35. So what's this area? How can we find it? We go to the table. 2.35. Let me just.
Doctor, this table will be given in the final?
Yes, if any exam or any quiz or any. So the quiz of next week, I will, if I ask you about, from the table, I will give it to you. It will be with you in the exam. Okay, so we said minus 2.35. So you go to minus 2.3. Can you see this is minus 2.3? And then at the top you go to 5. Let me remove these. Sorry. I'll just remove these. And then you go to the probability at the intersection minus 2, 3, 5. So this is the probability you are interested in. 0.009387. 9387. 0.009387. Let's do another one. Phi of minus 1.65, for example. Okay, minus 1.6, and again 5. I don't know why I use 5. Same. So it's 0.0.
Doctor, why you're choosing the minus 0.5 from the horizontal row?
Because this is the first digit, this is the second digit. If I want minus 2.93, so minus 2.9 and then 3.
Okay.
This is how you compose your number. Okay. So minus 1.65 will give you 0.049471. 49471. 49471. So let's see phi of, if I want 5.2 minus 5.2. Let's see how minus 5.2. What's the smallest number in the table? As you can see, the smallest number in the table is
minus 3.9.
no, minus 3.99.
Minus 3.99. Yes.
Yes. So this is the smallest number. What's the probability at that number? As you can see,
Almost zero.
almost zero. So the table gives you number starting at minus 3.99. Any number less than minus 3.99, and you can assume it has very, very low probability. You can assume it is zero. Okay, so table lowest number is minus 3.99. Any number less than that can be assumed to be zero. Okay, let's try some positive numbers. So how about phi of 0.79? So now phi of 0.79, it should be greater than 1/2, right? Because we'll cross zero, and then we will need all of that area. 0.79. Let's see. Okay, so it's so the following page gives for the positive numbers. So 0.79. So this is my 0.7, and I'll go all the way to 9. Then my probability is 0.785236. 785236. 785236. Let's do phi of 3.2. Let's see. 3.2. 3.2. So this is 3.2. This is 3.2. So 3.2, I do not have any number, so I go under 0. What's wrong? Not sure what's going on. So 3.2. This is 3.2, and then under 0. So it's the first column. So this is my probability, 0.999313. And again, largest number in table is, let's see, what's the largest number in table? What do you expect? $3.99. What's the probability at 3.99?
Largest number.
What's going on? Okay, so this is, sorry for this. I don't know it's behaving very funny.
Happens, doctor.
Okay, Murphy's law, not Murphy's law. Okay, so at 3.99, the probability is 0.999967. So it's almost 1. So any number greater than 3.99, you can safely assume it is 1. Is 399, which means any number larger than 3.99, its phi can be assumed to be 0. Okay?
Doctor, 1 or 0?
What?
0 or 1.
1 sorry. Yes, thank you. Wow. Yeah. وانا مصحصحين ما شاء الله عنكم. I'm glad.
بالك.
ها نشوف الصحصحة بالامتحان. So what I want to say is, because one of you wrote a good question in the chat, normal distribution should have mean of 0 and variance of 1. So the table that we have in our book and in the internet, you will always find it, is the table for the standard normal, which is mean 0 and variance 1. And now you can ask me, is this the only normal distribution that we'll face in our life? Of course not. So how can we use this table with other normal distributions? And the answer is standardize any other distribution that is not a standard normal. How to do this? I think I will not get into this in this lecture. We'll do it next time. But we'll see if we are dealing with, if you give me another normal distribution, has a mean of 5 and a variance of 9. And you ask me, what's the probability that that distribution is less than 2? We'll see how to convert that distribution to a standard normal, and we will see what's the equivalent of that random variable to be less than 2. What's its equivalent with the standard normal? We'll see, for example, it's like probability of x less than 0.1 of the standard. We go to the table, we find that probability, and then it will be exactly the same probability of the unstandardized normal distribution. So I'll stop at this point. I know we have a couple of minutes. If you have any questions, I will be happy to answer them. If you don't have questions, you are free to leave, and we'll continue with our normal distribution, inshallah, on Wednesday. We finalize it, and we do also the exponential distribution. But if you have any questions, please go ahead, and I'll be happy to answer.
Doctor, what will be the material for the next quiz?
It will be on using the table of normal distribution.
Okay.
It will be simple.
And Doctor, regarding to the midterm, the level of the questions, they'll